Okay, so now we're going to try to solve this problem. The question of where we have these two rigid containers. They're both of equal volume of 0.5 meters cubed each, and one contains 1.5 kilograms of air at 20 degrees C, and one contains 1.5 kilograms of water at 20 degrees C. And as we said, air and water are both fluids, but that's not really relevant to this problem. This is really a straight up thermo problem, so hopefully you were able to do it since you've already taken thermo. So container one is pretty easy, so let's solve that one first. In container one you have air, and air, as you know, is an ideal gas under most circumstances. So we don't really need to prove that yet. We'll just kind of check when we're done. If the pressure comes out sort of a reasonable pressure, we'll say, okay, it was an ideal gas as we suspected that it would be. Of course, for the ideal gas, we're going to use the ideal gas law. So PV equals mRT. Here we go. And we know a lot of these things. We know that V1 is 0.5 meters cubed. We know that the mass is 1.5 kilograms. And we know the temperature is 20 degrees C. And we also know we can't use 20 degrees C for temperature in this relationship, or really almost any other relationship. We have to use Kelvin. That's 293 Kelvin. So those are the three of our elements here, T1, V1, M1. You could put M1s everywhere if you want to put M1s everywhere. So that's that. And so what we don't have P, which is the thing we're looking for. And so far, we don't have R. Now, R, of course, is the gas constant. You all studied this in thermo. The gas constant can be easily calculated based on the universal gas constant. So we're going to find R is equal to the universal gas constant divided by the molecular mass, the molecular weight of air. The molecular weight of air equivalent, can be found in any thermodynamics table that involves these molecular weights, and you can find that the molecular weight for air is air equivalent is 28.97. So M for air is 28.97. That's the air equivalent. It's actually a mixture, of course, of nitrogen, oxygen, carbon dioxide, etc. But we can treat it as one. And when you calculate that R value, therefore, with the R value being equal to the universal 8.314 divided by 28.97, you get what I suspect is familiar to you at this point, 0.287 kilojoules per kilogram Kelvin. That is the R value for air equivalent. So that's our R value, and we plug all that in back into our ideal gas relationship. We have 1.5 kilograms of mass. We have 0.287 as our R value, kilojoules, kilograms, and Kelvin. We have 293 Kelvin, and that's all being divided by the volume of 0.5 meters cubed. So this is your mRT over V. Gives you P. When you crunch that through your calculator, you get P1 equals 252.3 kilojoules per meter cubed. Now you do have to be careful when you're doing pressure calculations that this is a kilojoule, so you need to maintain that kilo in front. We're going to try to convert this into a pressure unit. Joules are Newton meters, so you know joules are Newton meters because newtons are a force and meters are a distance, and force times distance is an energy. It's a work, so it's an energy. So that's what a joule is. It's a force times a distance. So that's a Newton force times a distance is meters. That's the units for the joule. And then I'm going to divide that by meters cubed. And of course that means that what I get for my pressure unit, which is a much more sensible unit for pressure, is that I get 252.3 kilonewtons per meter squared. So newtons per meter squared is the normal unit for pressure. And so we have 252.3, times 10 to the third newtons per meter squared. So that's the answer to the pressure in the box for container one. Now you can say, I did ask you, is the pressure different on the top and the bottom? you can expect, if you've done a lot of ideal gas calculations or gas calculations, that we are not going to see a difference in the top and bottom pressure that it is in any way significant. However, since it was asked, let's go ahead and prove that. We have time. By the way, I expect this video will go quite a bit longer than 7 minutes because it's a solution. And for solution videos, I'm just going to go as long as it takes. So we will just keep chugging, and you can obviously watch it in sections. Those areas that you don't need to know, or that you feel you already know, you can skip. All right, so we're going to look at the issue of the top and the bottom pressure here. And this pressure, what is the difference between the top and the bottom pressure? And so we know from static fluids, which you saw in a variety of classes, though you haven't studied in detail. It was covered probably in your freshman introduction to engineering class, at least for one, and certainly I would think in your physics class possibly again. But anyway, change in pressure for a not moving fluid, for a static fluid, is rho GH from top to bottom. So the deeper you are in the fluid, H is your depth or your distance from top to bottom. Your pressure difference across some distance H in a fluid is going to be rho, your density, times gravity, times H. So we're going to go ahead and figure out what the pressure difference would be in container 1 from top to bottom. Now, in order to do that, we really need to know the height of container 1, and we weren't given the height of container 1. What do you do? Well, obviously in a test situation, you raise your hand and you say, Professor Fowler, you didn't give us a height, what do I do? But in this situation, I'm saying, look, it looked like a box. I'm going to treat it as if it is kind of a box. The simplest box is a cube. So let's consider it a cube. Let's consider a cubic container. So in that case, we know that volume equals length cubed, right? Because that's the definition of volume in a cube. And I know the volume of the cube. The volume of the cube is 0.5 meters cubed. That's the volume of our container. And so that's equal to L cubed. And that gives me a side length of 0.794 meters. So that's going to be the height of our cube. It's going to be all the side lengths for our cube. Here's a great picture of a cube. And so, I've got 0.794 meters in height change if I go from the top to the bottom of my container. So I can calculate what pressure change that would be in air. So delta P equals rho, G, and H. I know H is now 0.794, or roughly that, depending on exactly how shaped the box is, but that's a good approximation. G I was given, and of course you probably know, 9.81 meters per second squared. And so what is rho? Well, rho in this case is very easy because it's just mass over volume. So the definition of density is equal to mass over volume. We were given the mass of 1.5 kilograms, and we were given the volume of 0.5 meters cubed. So that's pretty easy, and we can crunch that in the calculator. Actually, I don't even need a calculator. 1.5 divided by 0.5 is just 3. So we have 3 kilograms per meter cubed as our density for air. So the air in that box has a density of 3 kilograms per meter cubed, and we can then calculate a pressure change from the top to the bottom of the box. So we get 3 kilograms per meter cubed times 9.81 meters per second squared times 0.794 meters equals 23.4 newtons per meter squared. So is 23 newtons per meter squared a lot or a little? Well, the question to whether something is a lot or a little in engineering always depends on what you're comparing it to. If you're comparing this to a number like 1, then 23 is a lot. If you're comparing this to a number like 100,000, then 23 is not very much. In this case, the number we're comparing it to is the base pressure in the box. So the pressure we calculated using the ideal gas law, P of the air in the box, was 252.3 times 10 to the third newtons per meter squared. So this is, significantly greater. It's 4 orders of magnitude larger. It's a very small amount of pressure change. In fact, it's below the level of our significant figures. So we calculated 4 sig figs here for our air pressure, and this wouldn't even appear in that. So taking this, adding this, or subtracting this to this number would not actually change that number at all because it simply doesn't appear It doesn't appear at all because we don't have enough sig figs to even capture it. If you want to do this on a percentage basis, of course, you could take the 23.4 and you could divide it by the 252,300, and you would see that that answer is 0.000093. That is the pressure difference from top to bottom is 0.01% approximately of the pressure in the box. So clearly the pressure from top to bottom is not significantly different in air from the top of the box to the bottom of the box. Say air tends to have that situation. If you want significant pressure differences in a fluid like an air, like a gaseous fluid, you usually have to go significantly higher up into the atmosphere than say a meter. So all right, so we're not gonna. That was not an issue. The bottom pressure and the top pressure are the same, and they are both 252,000 newtons per meter squared. All right, so let's take a look at the other box. So the other box is going to be harder. Container 2 is harder to figure out. And actually, I think I've decided I will break this video. So I will stop doing this, and the next video will have container 2.